Hey everyone, welcome to Exponential Graphs. What we're going to be talking about is what these things look like and a couple of just other applications overall. So the first thing we want to think about is, what does an exponential graph even look like? We know what lines look like, we know parabolas, we know all sorts of stuff, but what do these things look like? And if you think about money, we can maybe draw a graph right here and say, what do we deal with money? And what you know about with exponential graphs is that it's like you take y equals a times b to the x, right? So that means we're going to say y equals a times b times b times b times b times b, a total of x times, right? So what we're going to be doing is we're multiplying by some number. So if we're multiplying by a number that's larger than 1, what's going to happen is that I start here, and then I multiply it by b, which gets a little bit bigger. And I multiply that by b, so that's going to get even bigger. And I multiply that by b, it's going to get even bigger. I multiply that by b. So it really starts to grow like that really, really quickly. Alright, so let's even just look at an example right here of what these look like. So this graph right here is y equals 2 to the x. Alright, so we have y equals 2 to the x. So if we only look at the positives for now, see how it just grows quickly and quickly, and we can zoom out, and it just really just grows very, very quickly, really, really fast. You see how when we get out to here, it's just flying up. Okay, so that's the general form of what our graph looks like. Okay, so what I'm going to do is I'm going to ask the question, what happens if we increase that 2? Right, so if I change this 2 to something larger, what's going to happen to this graph? I'm going to zoom back in, and let's just predict what happens when that 2 becomes something bigger, like 3.1, or just 3. What does it look like? If we say y equals 2 to the x, there's the blue one. The blue one is the original. The red one is our new increased base. And it just goes up faster, right? So even if I would say 2.1, does it increase faster? Yes, it does. But look what happens as we go out. It pretty much is the same thing. But it does increase a little bit faster. Okay? So we increase that base. It makes it steeper. Right. What do you think happens when we decrease our base? Let's say we change it from 2 to something less than 2. What do you think will happen? Well, let's put it at 1.5. It becomes a little less steep. That multiplication doesn't happen as quickly. Let's say it makes it 1.1. You see how way less steep it is, right? It's still going to grow. It's still going to grow exponential, but it's not going to grow as quickly. Okay, now I pick numbers all above 1. What happens if I pick a number below 1? What do you think happens then? Look at this graph. It goes the other way. You say, well, why does that happen? Why does it go the other way? Why is it increasing as I go to the left but decreasing as I go to the right? Well, if you think about this, we have y equals 0.5, which is 1/2 to the x. So if we make a table of values, x and y, if I have x is 1, 2, 3, 4, let's just pick those. Okay, so 1/2 to the first power is 1/2. 1/2 squared is 1 over 4, right? Because I can take this and say it's 1/2 to the third power, which is 1 cubed over 3 cubed, right? 1 cubed over 2 cubed. 2 cubed is 8, so really this would be 1/8. Which means these numbers are getting smaller because the denominators are getting larger. The numerators are staying the same. So this would be 1 over 16. Okay, so the things that you really need to know for this, exponential graphs, increase when the base is greater than 1, and decrease when the base is between 0 and 1. Now, why is 1 really the big key? Why do we even care about 1? Well, let's just put in the graph. Let's just put in 1 and see what happens. Hopefully it kind of makes sense, though. 1. It just goes right there. It's just this horizontal line. You know why? Because we're taking 1 and multiplying by itself. 1 times 1 times 1 times 1 times 1 doesn't change anything. So it's just going to be this horizontal line. So we don't care when that base is 1. That's not helpful, and that's not an exponential. All right? So there you go. So here's another question I'm going to ask you. And your question is the following. So this really gets into why exponentials are so important. It's all about investing and being able to have a lot of money. So the question is, you have $2,000 invested in an account. It doubles every 7 years. How long until this account has $1 million? So this is kind of a rule that you can go by. Usually it's called the rule of sevens, and that means usually investments will double about every 7 years. So if you're looking at 7 years, this is going to be right. So most accounts are going to double in that time. Now if your account does a little bit better, it might take less than 7 years. If it's a little worse, it might take more. But in general, this is a pretty good number. Okay, so what do we have to do? Well, we want to be able to set up an equation, right? I want to end with 1 million. And that's going to equal how much I start with, 2,000, times 2 to the x. Right? Right. Okay, so I really want to find out what is that x. Right? I need to know, what does x equal? How long is this going to take? Do I have time in my life to get to this $1 million if I start with $2,000? So I'm going to divide both sides by $2,000 first, right? The zeros all cancel out. And I'm left with 1,000 divided by 2, which is 500 equals 2 to the x. And I could say, okay, 2 times 2 times 2 times 2 times 2. I didn't really want to do that. I want to be able to actually use something else. So instead of writing this in exponential form, you have learned about logs. And so I want to write it in log form. So what I'm going to do with log form is I'm going to start with the base, go to the stuff that it equals, and have that equal the exponent. So I can say this is log base 2 of 500 equals x. And now I should be able to figure out what that is. All right. So my question is, what is that going to be? Well, let's just go through and let's plug it in. You can't see the calculator very well. Maybe I'll move myself over here. So what I'm going to do is, if I see this log button, that's going to be log base 10. Okay? Log base 10, that's just the log they use. This ln is going to be the natural log. We're going to talk about that later. So if I go to math, I go up on my calculator until this a says log base. That's really going to be helpful, because it's going to say log base 2 of 500. And then I will be done, and I get an answer of this. So I have 8.966 equals x. Okay? 8.966 equals x. Now the question is, what does that mean? Okay, so that means I have 8.966 values for x, which means x is not years. It's not going to be 9 years until you have $1 million. No, it's going to be 9 sets of 7 years, right? Let me move myself back over here. That's better. It's going to be 9 sets of 7 years, because we know that it doubles that 2 every 7 years. So you could also say this is like a 7x, right? Because we know that it takes 7 times every 1 year to do that. So we get 8.966 for x, which means what do we have to do in order to figure out how many years that's going to be? Yes, that's right. We're going to take that and we're going to multiply it by 7 to figure out how many sets of 7 years do we have. We have a total of that. So it would take you, let's go back to here, it would take you 62.75 years, 62 3/4 of a year. Dang it. There we go. 62.75 years to get $2,000 to $1 million. Now the good news is, hopefully if you have an account, you're not just putting $2,000 in and letting it sit. You're going to put some more money into it, which will make that number drop down considerably. Okay, so what we have is we know logs, we know exponents, and eventually we'll find out some stuff about e. All right, there you go.